We'll conclude our discussion of shortest path algorithms by looking at an example of the Floyd-Warshall algorithm. So once again, Floyd-Warshall is this dynamic programming solution that adds in a new vertex to the possible paths at each iteration. And it's basically building a new matrix of shortest paths that allows you to go through the first vertex and then allows you to go through the second and the third, etc. And we will look at how this works on the graph that we've been using for all of our examples here. Okay, the code for Floyd-Warshall, and actually I've made it a bit longer so that we can print out something. We don't need to print it or return a value, or declare a variable if we don't do that. The outer loop K is being created with a fold left operation. And so this just runs through the different vertices. And inside of here, what we're doing is we are tabulating the new matrix each time. So I and j are brought in by the tabulate as we build a new matrix. And each element of the new matrix is either the ij element that had been there before, or ik plus kj, the minimum of those two, whichever one happens to be the better route. Okay, so I have that graph inside of this code, and we can run it and look at the result. So there are lots of matrices being printed here. The first one is our initial connection matrix. So it is nothing more than this graph here. Okay. What should happen after one step through that? So after the first step through that, what we do is we add 0 as a possible intermediary. Okay, so let's look at this. How could you improve things if you're allowed to go through 0? Well, that will impact the routes of the things that head in to 0 for this first step. It winds up having more of an effect later on as we go. But so previously we couldn't get from 6 to 1, but now we should be able to go from 6 to 1 through there and then there, because 0 is allowed as an intermediary. Similarly, we should be able to go from 2 to 1 along that path. We can also get to 3 and 4. So whereas previously our original matrix, the entries at 2, 1, 2, 3, and 2, 4 were all infinity, and 6, 1, 6, 3, and 6, 4 were all infinity. Now they should have other values in them. And we can go look at the code and see here is the row for 2. 2, 1 we can now get to in 3. 2, 3 we can get to in 1. And 2, 4 we can get to in 2. 6, 1 has the 6. That was the edge with a length of 3, followed by another edge with a length of 3, and a 4 and a 5. So sure enough, we have added some additional values into our matrix that are smaller than infinity. The next step is to then do the same process where vertex 1 is an intermediary, building on this matrix. And so we get another matrix that has a few more values filled out in it. And then we go down and we're slowly adding in additional ones. You can see that by this point most of the infinities have disappeared, and we get the exact same matrix for the answer that we had in our with our previous code. So that's tracing through Floyd-Warshall and what it does for matrix, as well as a simple solution in the Scala programming language. And that concludes our coverage of shortest path algorithms.